Okay, so in few minutes, for few minutes we are going to derive some results of thermodynamics. So what you have to do is, you have to be ready for next few minutes to just keep writing. So this is a lecture type of thing, there is no problem. We are going to derive some results, you have to copy those results. Now the first result is entropy change in expansion, isothermal expansion. So I have a isothermal expansion process. Entropy change is given by, that is delta S nr ln Vf by Vi, where Vf is the final volume of system and Vi is the initial volume of system. So what is Vf? This is final volume. So Vf is final volume. Are you getting or not? And what about Vi? This is the initial volume. So this is your initial volume. I have to derive this result. How can we derive? Can anybody give me any idea? If you remember, delta S is, so we have expression for delta S. Delta S is basically a state function, and expression for this is Q reversible by T. So delta S is given by Q reversible by T. Did you remember this result? Now what is my target? Is the process is isothermal, so temperature is constant. Isothermal process, so temperature is constant. I have to only find Q reversible. If I am able to find Q reversible, plug the value of Q reversible here, and then I will get the delta S. To find out the Q reversible value, I will use first law of thermodynamics. What is the first law of thermodynamics? Is delta E is equals to Q plus W. That the change in internal energy, delta E, is equals to heat change plus work done. Are you getting or not? So this is, in this notation I have taken, heat given to the system is positive, work done on the system is positive, change in internal energy the system is positive. So if it increases, it's positive. So this is the convention I am following. Now if the process is isothermal, temperature is what? Constant. So I can say dt is what? 0. So if the process is isothermal, I can clearly say dt is nothing but it is equals to 0. Are you getting or not? So if dt is 0, I also know internal energy change, that is delta E, is given by NCV dt. So if dt is 0, then NCV dt also becomes 0. Are you getting or not? So NCV dt is 0. So change in internal energy is 0. If I plug this value in this equation, that is delta is equals to 0, this equation becomes Q is 0 is equals to Q plus W, or Q is equals to minus W. Are you getting or not? Now, if my system only does expansion work, because volume is changing, volume initial volume is Vi, final volume is Vf. So let us assume if my system only does expansion work, that is it goes from Vi to Vf. For expansion work we have expression, that is minus P dV, that is the expansion work is given by minus P dV. If you remember this, we have derived this equation in the class. Work done is equals to minus P dV. Minus sign comes because if you increase the pressure, volume will decrease, and to basically balance the sign this side and this side, I have to plug a minus sign. If you remember the class, we have derived this thing in two courses. When you have a compression situation and when you have expansion situation, in both cases you have to plug a minus sign, and that's why this minus sign comes only because of the convention. So work done is minus P dV. Basically here we have external pressure. This pressure is external pressure. If you see your copy notebook, you will find. So now I can write from this equation, let us take a small q. So this is a small q, so I can write dq is equals to minus dw, and dw is, I can write p dv, so minus minus cancels out, so I will have plus p dv. So dq is equals to p external dv. Now if the process is reversible, if the process is reversible, I can say P external is equals to P internal. External pressure and internal pressure are same. In that case, I can also write internal pressure can be given as PV is equals to nRT. If I apply ideal gas equation, internal pressure can be given simply by this equation, that is nRT by V. Are you getting? Are you agree with me or not? Because what I am saying is, I am saying if the process is reversible, in reversible process, system and surrounding always remains in equilibrium. This means there is no net force on the boundary. So if the boundary, the internal pressure is Pi, then outside pressure is P external. So in that case, P external should be equals to Pi, because there is no pressure gradient at the boundary. There is no pressure difference at the boundary. If there is a pressure gradient, in that case there will be a force. If there is a force, the system is not reversible. So this is a criteria for reversibility, that is external pressure has to be equal to internal pressure. In that case, P internal can be given as nRT by V. Now if I plug this value, so now I can write dq is equals to P external into dV. P external is same as P internal because the process is reversible, and P internal is given by nRT by V. So now I can write dq reversible is equals to P internal into dV. P internal is given by nRT by V into dV. Up to this point, anybody having any confusion? No confusion. That's good. Now see, we have expression for ds. ds is what? dq reversible by t. q reversible by t. So now I know the dq reversible. I can find ds. So ds will be dq reversible by t. dq reversible is nRT by v dv. So this becomes t. t goes out. So nr by v dv. Are you getting or not? Now if you integrate this ds from internal entropy, initial entropy Si, final entropy Sf. So this is the final entropy, initial volume to final volume. If you integrate, so this will become Sf minus Si, Nr dV by V ln V. So ln Vf, V2 minus V1. So everybody knows ln Vf minus Vi can also be written as ln Vf by Vi. So if you plug this value here, you do some mathematical calculation. If you plug this one, you will find nRT Va by Vi. So you see, entropy change in isothermal reversible expansion is given by Nr ln Va by V. Molar entropy change will be given simply R ln Vf by Vi. Now if I want to find entropy change in joule unit, you have to take R 8.31. If you want to find entropy change in calorie unit, you have to take R 2 calorie. Are you getting or not? So this is we have discussed how the entropy changes if the volume is changing, and the process of course is reversible isothermal. So this you have to remember. So you can remember that entropy change in isothermal expansion is given by nRT. Now you see, if this is compression case, then entropy change will be negative. Vf will be lower and Vi will be smaller, so this will be negative. If this is expansion case, Vf is greater than Vi. Vf is greater than, this means this number is greater than 1. ln 1, this means greater than 1, so this will be positive. So if expansion, there is a positive entropy change. That obvious. We have already discussed. If there is something increase in volume, there is a change in entropy that is positive. There is decrease in volume, there is a change in entropy that is negative. So for compression, entropy change is negative, but for expansion, entropy change is positive. Are you getting? Okay, good. So we'll go for the next derivation, something related to entropy again. Now, so let us stop here. We'll go for the next derivation.